Hi Holly, some comments on your arrow pushing and your resonance structures. On the first problem, the HNO3, you had three structures drawn, 1, 2, and the one that you have labeled as 3. Numbers 1 and 2 are good structures, and the arrow pushing that you had in number 1, which I've tried to replicate, is correct. So an oxygen which was negative with 3 lone pairs, one of those lone pairs is transferring to nitrogen to explain the double bond nitrogen and explain how the oxygen reduced from 3 lone pairs to 2. When that new pair comes to the nitrogen, then a pair that nitrogen was sharing with the top oxygen moves to the top oxygen, double bond becomes single, oxygen becomes more negative, and the oxygen moves from having 2 lone pairs to 3. Those are the standard 2. They're perfectly equal resonance structures for that molecule. The real molecule is a hybrid of the 2 of them. Neither is major because they're equally good, the same number of bonds, the same kind of negative charge on oxygens, formal plus on nitrogen in both cases. Your resonance structure 3 does qualify as a resonance structure, but it's not really a particularly useful one. This would make a negligible contribution to the real hybrid, and we would not, bother to draw it. In the structure, every one of your atoms has a formal charge. So we don't want to normally unnecessarily have abnormal formal charged atoms. So now your oxygen should be plus, your nitrogen should be plus. Both of the outside oxygens are negative. In the structures on the left, we have just 1 plus and 1 minus. 1 plus and 1 minus on number 2. But now everybody is either plus or minus, and we would prefer to avoid that if possible. This is typical of an allylic, so numbers 1 and 2 are typical of an allylic type system. When you have a charge on an atom, in case 1 the oxygen on the bottom, a charge next to a double bonded center, the position of the double bond is likely to flip over and the position of the charge moves to the other end, to the other oxygen in that case. But you're involving 3 atoms in the process. For the formula underneath, the H2C double bond CH CO2 minus, I have drawn the 2 appropriate resonance structures, numbers 1 that you had drawn, your first one drawn, and number 5 which you had not drawn. This is another example of an allylic system where we have a charged oxygen. In number 1, it's the oxygen on top is charged next to a double bond, the C double bond O. When we draw the revised resonance structure, we flip the double bond from the bottom oxygen to the top oxygen, the charge from the top single bonded abnormal oxygen to the bottom single bonded abnormal oxygen in picture 5. The arrow pushing is shown, is illustrated in both of these for going from 1 to 5 and then for 5 going back to 1. You had structures 2, 3, and 4 drawn. Each of these has some problems. In your structure 2, there's 2 issues. There's no reason to have a negative charge on the bottom oxygen because it has perfect bonding. 2 bonds, 2 lone pairs. That's standard normal bonding for an oxygen. So no reason to assign... Oh, nope, I'm wrong about that. I'm looking back at your structure. You actually drew in 3 lone pairs on that one. So that would have charge, except that you're violating octet rule. So the oxygen has 10 electrons, can't have more than 8, and the carbon has 5 bonds. The normal bonding for things and the octet rule were discussed in the notes on pages 1 and 2 of the first day of lecture. and you want to make sure that you remember the octet rule max and the maximum number of bonds, lone pairs for any of these second row elements. In structure 3, again you have an oxygen that exceeds octet rule, so that's not possible. In number 4 you have an oxygen which exceeds octet, and you have a carbon that exceeds octet. So none of these are actually feasible structures to be doing. I think you're perhaps making things more difficult than you need to, and I'm going to see if this works for my process. My computer died yesterday, so my technology here is not what I'm used to doing. But in most of these resonance situations, what we have at the core are 3 atoms, 2 of which are double bonded to each other, and the third of which would have some kind of a charge. So whether that's a negative charge or a positive charge, those same 3 elements or those same 3 atoms will then have a resonance structure in which you could just as well have drawn your bond from the middle to the right carbon, doubled, and put your charge on the opposite end of the threesome. That's the standard 3-atom, 2-resonance structure layout that we'll see frequently and need to account for most often. And usually in this sort of a case, whether it's an oxygen lone pair, a nitrogen lone pair, or a carbon lone pair, what's happening in the anion situation is that a lone pair goes to the middle carbon and pushes a bond out from the position 2 to position 1, becomes a lone pair negative. In the reverse direction, those 2 electrons come back towards 2, become a pi bond, and push the 2 electrons that were shared between 2 and 3 back over to spot 3. In the cation type case, it's not a lone pair that's moving, but it's a pi bond which moves, and when that creates a new double bond, that leaves a underbonded atom elsewhere. But we want to simplify our focus and try to, you want to be able to recognize there are some other exceptional situations where resonance is somewhat at play, but 95% of the time it's these kind of allylic situations, an oxygen on the end, 2 oxygens, in which you're using the same 3 atoms and you're switching the location of the double bonds and switching the ends that has the charge. Okay, good luck. Hope this is slightly helpful.